Hello students. Today we will discuss about differential relay. In our past lecture we have done our numerical related to discrimination of faults, current transformers, potential transformers and overcurrent. So in this lecture we will basically focus on differential relay, its construction, applications and its operation. First we have to understand about what is a differential relay. Well, a differential relay is defined as the relay that operates when the phase difference of two or more identical electrical quantities exceeds a predetermined amount. The differential relay work on the principle of comparison between the phase and magnitude of two or more similar electrical quantities. Let's say for the example, if we want to define the practical example of differential relay, consider the comparison of current entering a protected line and the current leaving it. If the current enters the protected line is more than the current leaves it, then the extra current must flow in the fault. Now, this difference between the two electrical quantities can operate a relay to isolate the circuit. So, if we can define it more simply, then we can say that any change occur between two same quantities, the differential relay will measure it and it operates according to the predetermined value. If we talk about the types of differential protection, so we can say that there are two fundamental systems of differential or balance protection that we can say. One is current balance protection and the other one is voltage balance protection. And specifically, if we divide it, so we have three categories. Number one, we can say current balance protection, or the other name is current differential relay. The second one is voltage balance protection or voltage differential relay, and the third one is biased or percentage differential relay. In our next slides, we will discuss each of that type with proper example and explanation. First, we will discuss about current differential relay. As you can see in the figure, which shows an arrangement of an overcurrent relay connected to operate as a differential relay. A pair of identical current transformers are fitted on either end of the sections to be protected, and the secondaries of the CTs are connected in series. Well, they are connected in such a way that they carry the induced current in the same direction. Well, the operating coil of the overcurrent relay is connected across the CT secondary circuit. So we can compare the differential relay, the current at the two ends of the alternator winding. So under normal operating condition, as you can see in the figure also, we have suppose an alternator winding carries a normal current of 1000 ampere, then the current in the two secondaries of the CTs are equal. Well, these current will merely circulate between the two CTs and no current will flow through the differential relay. Remember, this is very ideal condition. If we talk practically, uh, this is very much difficult, and if we can say if both conditions are 100% balance, uh, this will be near to ideal condition. In next conditions, we will check what is the practical conditions we have to deal with. We have two examples of different circuitry, so we will check in next slide. So in the first figure, you can see if if the current around 500 ampere in the condition 1 flows out of one side, while a larger current of 2000 ampere enters the other side, as you can see in the figure. Then the difference of the CT of the secondary current, we can say that 10 minus 2.5, that is equal to 7.5 ampere. Now, uh, the 7.5 ampere is the difference in this. If we can talk in simple words, the 7.5 is the difference that will flow through the relay. So, if the system is set that a predetermined value higher than the 7.5, so it will not operate. But if the system is set at the value below 7.5, so at this case the relay have to operate. So it's all about the predetermined value that the user sets. If we see this condition, so this condition is different from the previous one, the condition number 1, because in this condition the current is flowing to the fault from both sides. So uh, the sum of the CT of the secondary currents, we have to add them, so it will become 10 plus 15. Now this 10 plus 15 we added, and so our difference become 15 ampere. So same as the case like condition 1, if that 15 ampere is the value that has been set by user, that exceed a certain value, so the relay will operate. And if it is set below 15 ampere, the relay will not operate. So the direction of the current is important. As previously you see in the condition 1 that the direction of flow of current is different, and in the condition 2 the direction of flow of current is different, but the methodology is the same. There are some problems, or we can say the disadvantages related to this current differential relay that we have to face when we apply this type of protection. So number one is the impedance of the cables generally causes a slight difference between the currents at the two ends of the section to be protected. If the relay is very sensitive, then the small differential current flowing through the relay uh, may cause it to operate even under no fault condition. Well, in this condition, if we have cables of long length, so the impedance of the cable um, get vary, and through that difference, we have serious concerns on our current flow, and that may operate the relay under even in no fault condition. The second one is the pilot cable capacitance causes incorrect operation of the relay when the large through current flow. Uh, the pilot cable, first we have to define that. The pilot cables are basically used for control, protection, signaling, telecommunication, data transmission purposes. You can say that are associated with power distribution and transmission. systems. Along with that, such systems are mainly operated by electrical supply industry, and similar application occur in industry. Uh, so um, the capacitance of that cable also cause incorrect operation of the relay, because as we see that this specific type of relay is basically based on the difference between the two currents. So if there is a difference, so that will exceed a predetermined value, it have to operate no matter what cause. For example, we can say that it have a true fault or a false fault call. Thirdly, the accurate matching of the CTs cannot be achieved due to pilot circuit impedance. As we all know that while manufacturing, there is always a difference between two CTs, and two cities through different wire impedance. So we cannot match, for example, 100% two different type of cities. There are some remedies through which we can solve these problems, but we have to know that these are some critical areas that we have to focus on, and while working with this current differential relay. Well, the next type is voltage balance differential relay. As you can see in the figure, which shows an arrangement of voltage balance protection. In this scheme of the protection, two similar current transformers are connected at either end of the element to be protected. In this case, we have, like we can say, we have alternator winding by means of a pilot wire, and the secondaries of the current transformers are connected in a series with a relay in such a way that under normal conditions their induced EMF are in opposition. For example, we can say we have two conditions. Like if we talk about healthy condition, so what will be the healthy condition? We can say uh, if the two currents I1 and I2 that you can see in the figure, both are flow in the primary windings and both are equal. Therefore, the secondary voltages of the two transformers are balanced against each other, and no current will flow through the relay operating coil, because there is no difference and both currents are same. Now, what is the second condition that we can say that the unhealthy condition? As you know, when a fault occurs, the current in the two primaries will differ from one another, because there are, for example, they have two currents I1 and I2, and both are not equal, and we just say that there is a fault. So we can say that if I1 and I2 are not equal, and the secondary voltages will no longer be in balance. So this voltage difference will cause a current to flow through the operating coil of the relay, ultimately which closes the trip circuit. So this is very simple and very easy to understand the operation of voltage balance differential relay, and you can just see this figure and you will understand the whole picture. Just focus on the two conditions, that if the both current are balanced, like I1 and I2, and the second one is if they are unbalanced. So we can also say it is not necessary that If a very low amount of current in unbalance occur, so the relay will trip. This will not happen. This is according to uh, our setting. The setting is basically our predetermined value. So the relay has to exceed that point to get in operation. Well, the disadvantages related to that voltage differential relays and the problem we can face are: the first one is a multi-gap transformer construction is required to achieve the accurate balance between the current transformer pairs. So it will increase our cost. Secondly, the system is suitable for protection of cables of relatively short lengths due to capacitance of pilot wires. Well, on long cables, the charging current may be sufficient to operate the relay even if a perfect balance of the current transformer is attained. Uh, in this point, or the second disadvantage that we have seen, uh, that is the capacitance between the cables. As we see that if we talk about the transmission lines and the transmission lines of long distance, so between two different cables, the capacitance phenomena occur. So due to that capacitance, the voltage levels can change, and that voltage have the tendency to operate the relay. So we can say due to that capacitance problem, a false operation could be performed. So this is the drawback. So we can use this relay in a short length cable, or if we want to use in long cables, there are some measures we have to take in account in order to uh, rectify this problem. Well, the third type of differential relay is percentage differential relay. Well, the percentage differential relay, we may define this as a relay that operates on the phase difference of two or more similar electrical quantities. Well, it is the advanced form of differential protection relay. Well, if we talk about this percentage differential relay operation, uh, well, the percentage differential relay is basically designed to respond to differential current in terms of its fractional relation to the current flowing through the protected section. You can see in the figure there are two CTs, and just for the sake of example, these are installed on an alternator winding. In the figure, which shows the uh, basic construction of this relay, you can see it is essentially an overcurrent balance uh, type of relay with an additional restraining coil. Well, uh, here the working of the and the major work of the restraining coil, it produces a bias force in the opposite direction to the operating force. As we can see that under normal conditions and load conditions also, the bias force due to restraining coil is greater than the operating force. Therefore, the relay remains inoperative. When an internal fault occurs, the operating force exceeds the bias force. Consequently, the trip contacts are closed to open the circuit breaker. So, In this case, the bias force can be adjusted by varying the number of turns on the restraining coil. Now we can see that how the operation is performed. As you can see in the figure, which is the equivalent circuit of that bias beam relay, you can this is the second name of percentage differential. The differential current in the operating coil is proportional to I2 minus I1, uh, because here the basic law, that is KCL, applies here, and the equivalent current in the restraining coil is proportional to I1 plus I2 over 2. Since the operating coil is connected to the midpoint of the restraining coil, it is clear that greater the current flowing through the restraining coil, the higher the value of the current required in the operating winding to trip the relay. While under a heavy load, a greater differential current through the relay operating coil is required for operation than under light loaded condition. So this is very simple operation uh, that this on which this percentage differential uh, relay operates. This relay, as we mentioned earlier, you can call it percentage relay, you can call it beam bias relay. That is because the operating current required to trip can be expressed as a percentage of the load current. So you can also call it percentage relay or beam bias relay. Both terms are correct. Well, we use the slope percentage, and we can find that the slope percentage of the differential relay. But the first question is that why we find this? The slope characteristic provide high sensitivity well when low level of currents are flowing in different zones of protection, but also it has less sensitivity when high level of currents are flowing and false differential current due to the current transformers. CT saturation is more likely. As you can see, the slope percentage of differential relay is basically depends upon the differential currents, and the second one is over average currents, that basically in terms of secondary current that is flowing in the protection zone. So as we see in percentage differential protection, we provide a slope feature to the differential protection relay, as we mentioned earlier. So uh, a typical slope characteristic you can see in the figure. Well, there are two axes, x and y. Well, you can notice an offset uh, off to the account for the no load current of the transformer. Well, this is basically example of an transformer. If we don't provide this offset, then the differential protection will operate during no load of the transformer, and the transformer will trip the and the differential relay will trip the transformer primary side breaker, which is not desired. As you can see, the current on the x-axis is the average current of the primary and secondary windings referred to primary. It basically indicates the restraining current called the biasing current, as we studied in the last section, that is a bias beam relay. You can see the current, while the corresponding difference on the y-axis represent the differential current. Uh, that differential protection relay will pick up if the magnitude of the differential current is more than a fixed percentage of the uh, restraining current. So, this is very important to understand, and you can see in the graph that where the relay will operate and where it will not operate. Well, collectively, if we talk about the differential relay, like we have discussed the disadvantages of current and voltage differential relay, we can see that under healthy condition, there may exist a difference in secondary current even for identical current transformer due to CT errors. So in practice, there will be differences in the magnitude and the phase of the currents entering and leaving the zones of protection. Well, the current transformer characteristics are not perfectly matched at some stage. So this is one drawback that we have also discussed earlier. Similarly, under severe fault condition, the current transformer may saturate and cause unequal secondary currents. So, if this difference exceed the relay pickup value, that you can say the I pickup, then it may cause an unwanted tripping of the differential relay. So we have discussed the different remedial action we can take on this account to overcome this problem, to operate the relay in proper manner, because if there is any false tripping is performed by the relay, so it will hurt the all the credibility of the system. Along with that, if that relay is so much critical and the position of that relay is very much critical, so the whole system can also be stopped. So we have to be very careful, um, because we have to see the different faults and different conditions and different drawbacks. We have to solve that, and we have to take in that faults in consideration while designing our protection system. We can also solve the problems related to data specific CT ratio issue, so we can understand this concept fully. As we discuss, the drawbacks and the problems occur while using the differential protection schemes. So here is one more example of the CT mismatch, and we can see practically that how it will damage our system. So let's take for the example, as you can see in figure, you have a balance current like 200 amperes that is entering and leaving the node, and you can say that it is a balanced system ideally. But if you look at the CTs, one CT is 200 by 5.1 ampere and the other one is 200 by 5 ampere. Remember, this is an example and of the relay that is installed on the alternator winding. So as you can see that both currents are same. So as we studied in our uh, last slides, that if the both current are same, so ideally there will be no current in the operating coil. But here you can see there is a current of 0.1 ampere. This 0.1 ampere is basically due to the mismatch of the CTs. If the CT get mismatched, then it will cause problem. So you can see the both currents are same. Ideally there will be zero current that have to flow in the operating current, but there is a current that is 0.1 ampere that is flowing. So if we focus that what is happening, that the CT, both CTs are mismatched. So one is 200 is to 5.1 and the other is 200 is to 5 ampere. So 5.1, if we minus 5.1 minus 5 ampere, so uh, the 0.1 ampere will flow into the operating coil. Now at this stage the relay will not operate, because as you can see the pickup current is 1 ampere. So what will happen next, we see in the second condition. Now we have the same circuit, we have the same CTs that we used in the last slide, but now the one condition is changed, that is the flow of current. We have seen that we have the same currents uh, in the last slide, but in this slide we have two different currents. As you can see, you have 235.3 ampere at left hand side and you have 200 ampere on the right hand side. Now what will happen? The CTs are same, 200 by 5.1 and 200 by 5 ampere. As you can see that when there is a current that is 235.3 ampere flows on a system and there is a mismatch, so as you can see the 6 versus 5 ampere, if you minus 6 ampere with 5, uh, you can see the 1 ampere current will flow through the operating coil of the overcurrent relay. Now this condition is absolutely false, because this is due to mismatch. The relay will have to trip on some other point because it is a mismatch of even a 0.1. So this problem cause early tripping, and we can also say that it is a false tripping. So if this relay is installed on an alternator winding, so what will happen? It will trip it. So at this condition, a false operation and a false tripping is performed due to this CT mismatch problem. Now, one more example that is directly linked to our first case. In this condition, you can see you have both currents are same, that is entering or leaving. You can say an ideal condition, but just for the sake of example, we have the same CTs of same current ratio like 200 is to 5.1 and 200 is to 5 ampere. Now what will happen? Due to this mismatch, uh, for example on 5.1 side there is a 51 ampere current, and on a for 200 is to 5 ampere side there is a 50 ampere current. So if we minus then 51 minus 50, the 1 ampere will flow through the operating coil of the overcurrent relay. And as you can see, the pickup that have set for this alternator winding is 1 ampere. So at this stage, a false operation is performed even in an absolute balance case. So in this figure, you can see if the current magnitude is increasing, the small mismatch can cause a huge problem. Like if we can just for the sake of example, we have 20,000 ampere on both sides. So what you think, what will be the current? The current will the operating coil will in you have more current in that. So you can see the increasing magnitude will cause more problem due to the mismatch. So in a nutshell, we can see that even a zero point 0.1 ampere or is very important in this differential protection scheme to avoid any false operation or false stripping, because as I said earlier that these false stripping will cause damage to the device, also to the whole process, because the whole system get stuck, and the whole if the whole system get stuck, it will stop the complete process, and you have to uh, recheck again and again, and it will cause severe problem. Well, the application of the differential protection uh, is very vast, and that the differential protection can be applied for the protection of generators, motors, bus bars, transformers, and line protection, but specifically in case of alternators, motors, and transformers, uh, or those devices that contain windings, the differential protection is widely uh, used. Along with that, as we see in our whole lecture, that we take example of the windings that is of basically alternator winding. Same is the case with transformer. So the transformers case, bus bar case, line protection, we will study in detail each component protection in our upcoming lectures. Students, that's all from the differential protection side. In next lecture, we will discuss about distance protection. Thank you.